So let's talk about resistors. What I want to do is I want to have just a few slides that I have here on kind of why we use resistors, what they look like, what the types are, and some applications. And then I'm going to jump right into the color codes. So if you're here just for color codes, just slide forward a bit until you'll see I'm talking about color codes. So let's just jump into this and talk about what resistors are and what we do with them. They're really cool little things. They resist current. Because they're resistors? Yeah, that's their whole thing. I kind of like to say they throttle current, although don't tell anyone when I say that, because that's a term that's used in fluid power. But it's nice to kind of understand, current in kind of imagining it's water or liquid or air or something. So it's almost like if there's a pipe going and we restricted the pipe, that would slow down the flow. Well, essentially, resistors do the same thing with electrons in a wire. Pretty cool. So we can do a lot of things with these. We can do some speed control. I've got some circuits to show these things. We can do power control. We can vary voltage. Actually, we can take voltage from a source and divide it up. It's pretty cool with resistors. And we can also vent excess heat and excess power. So you don't want to give as much power to something. You can actually steal some of that power away from the power source, like the battery or whatever the power source is, and just vent it into heat into the atmosphere. You can also actually just do that specifically by just creating heat. I mean, sometimes we need heat. Let's take a look at some of these applications. So in this case, what we've got here is we've got a voltage divider. So if I look at this, I've got just a battery here. Let's say that's a 10-volt battery. And I actually wanted 5 volts. I didn't want 10 volts. I wanted 5 volts. I can tap into it. Or maybe I wanted 3 volts, or 2 volts, or 8 volts, or 9 volts. Depending on what the values of these resistors are, if I tap into this area, kind of in between them, I can actually get a different voltage out. It's pretty cool. Now, that's not a really good application for high current, but if we have a device that's really low current, that's a really good application. You can actually kind of have a variable DC power supply as long as you're dealing with really low current. Now, we'll actually go into that in this course. So let's just move on and take a look at this application. This is speed and power. So what I've got here is I've got a 3-way switch. Now, I also have this switch because I have to be able to turn this on and off. So I close the switch, and then I can go from this setting to this setting to this setting. If I put these at different values, then they're actually going to steal some of the voltage that goes to the motor. So that eventually the motor will actually essentially, the motor will drive at 3 different speeds. I can put it at this speed here, which is full speed, or I can go to here or to here. That's actually how the fans work in your car. Click, 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 the fan speeds. And over here, I can vent power. So I close the switch, and the motor runs at full speed, and it's good. And maybe I actually have, for some reason, my voltage source has gone up a little bit. And I don't want to put that much voltage into my motor. What I can do is close this switch. This will steal some of the power in the circuit and actually vent that into the just atmosphere. It'll create some heat. I keep adjusting my glasses because I have a thing that's broken. So anyway, don't let that distract you. Let's move on. I could have a heater in a tank. And I just have a process here, and I need a heater. Essentially, heaters, all electric heaters are just resistors. They're just actually stealing some of the energy and turning it into heat. We'll talk about voltage, in this course a little bit later and how that actually happens. But that's what's going on here. It steals the energy from the voltage and it turns it into heat. It's pretty cool. So we can take a resistor like this and put it in a tank like this. And that's how heaters work. That's what we can do. And even, I remember kind of years ago at the cottage trying to build a box where we could keep water from freezing in the winter. And what I wanted to do was just put a few resistors in there, a few like 5 or 10 watt resistors in there, and insulate it and just run some 12 volts through them. So they're just producing 5 or 6 watts, but they're enough to make sure the water temperature doesn't go below 0. Never actually built it. Okay, let's move on. So these are different types. So we have a few different types essentially, and we have 2 that we'll see in components, and they look like this. I'll go back to that other slide. They look like this. So we've got this guy and this guy, and these guys, these have more accurate values to them, but they're not as good at dissipating heat. So they're metal film resistors. But if we look at a carbon composite resistor, those things, they're really good at, you can get them really hot. You can get them like super hot, and they can dissipate that heat really easily. Well, not really easily, but fairly much more efficient than the carbon film can as well. But the thing is, they don't make these really accurately. They can't really make them really accurately. So it's a trade-off. You got one or the other. Let's go back to this other slide here. I also wanted to say that we have little tiny resistors that we actually just put on breadboards, and they're called surface mount resistors. And they're not going to be designed to get hot. I mean, all resistors will produce a small amount of heat, but the ones in the circuit here, they're really just used to divide voltage and kick the voltage down so that different components have different voltages. And we also use them to limit current. And one thing is in a timer circuit, what's going on there is that we have a variable resistor that varies the flow rate or the current into a capacitor, and then it takes a certain amount of time to fill that capacitor. So if I increase the resistance, the flow, or I'm throttling the flow rate. Again, don't tell anyone I said that. So I'm slowing the flow rate down with this resistor, and I can increase that so it takes a long time to fill that capacitor. And once that capacitor gets to a certain voltage, it triggers the circuit. Or I can lower that resistance quite a bit, and then the flow or the current into the capacitor is a lot higher, and it fills more quickly. So you'll see those in circuits as well. Really, really cool. And this is just essentially, they're all different kinds of ceramic. We call this a ceramic or high watt resistor, and they'll either have coils on them or they'll have a coil inside, and you really can't see that, but they're all made of ceramic because ceramic can hold a lot of heat. So these guys, their whole purpose is just to vent heat, just get rid of excess power. Okay, let's jump on to potentiometers. Really, really cool things. So this course, we're going to go in much more depth into potentiometers as we go, but for now, welcome to potentiometers. What we're going to do is we're going to say there are two kinds, and here is one is a tangible type. I can put a dial on there. You can actually stick a screwdriver in there. You can actually just take that with your finger and turn it as well. But those are for adjustability. Those are for human interface. It's just the human's going to go over and adjust something, whether it's a volume dial or a dimmer dial, all of these really cool things. Time adjustment for sure, speed control, dimmers, circuit adjustments. So what the circuit adjustments is this. It's a trimming pot. Trimming pots, you'll find them in circuits. If you go to rip an old, whatever, any kind, not old, I'm saying go to Value Village or whatever, or some place, Sally Ann, or some place that sells cheap electronic equipment. And just get an old clock radio or any kind of device, even an old telephone or something. Take it apart, and you'll see they have trimming pots on them. And the reason they have trimming pots is because, you know, when you design and do the math for a circuit, you say, okay, I need a 740 ohm resistor here, and or 720, and this and this. You put those in, and they're not exactly those right values. So to make the circuit run just right, you got to go in there and just kind of change the resistance a little bit. And you do that with a trimming pot. So you put a trimming pot in the circuit, you go over and adjust it with a tiny little screwdriver, and when you're done, you put a little piece of glue on there. So you'll see when you rip these circuits apart, you'll see potentiometers in there. Sorry, you'll see trimming pots in there. And often they'll just have a little dot of glue on there just to stop them from rotating. Really cool. So they're for circuit adjustments. And then there are a bunch of different kinds of those. Now, control discussion. So this is just a control discussion about how we maybe use a couple of resistors to control the speed of a motor. This is another, this is different than this one. Take a look. So I've got three different options here. No resistor, or this resistor. But over here, I've got another circuit. So, you know, you can build control in lots of different ways. I've got resistor 1 and resistor 2. If I don't close either of these, the current has to go through both of these. So the throttling, I gotta stop saying that, but there you go. So the current is slowed down quite a bit. Or if I close this, it's only being slowed down by this, because the current goes here, it flips over here, and it goes in, it's forced to go through this resistor, and then it goes there. This is also stealing some of the voltage. It's not only slowing down the current flowing through the wire, it's actually stealing the energy from the voltage. Now there's less voltage for the motor, so I'm controlling the motor. So think about how many different kinds of speeds I can get for this motor. And if this is closed, how many different kinds of speeds can I get? Just food for thought. Okay, so now labeling, and then we'll get right into resistor color and how to do the color codes. So essentially what's going on here is I just want to let you know that when you go to the store to buy resistors, or you're going through your bin and you're just looking for old resistors, or you're finding some resistors somewhere, if they're really large, they'll be labeled like this. So this will be a 22 ohm resistor. Over here, this is a 2.2 mega ohm resistor. And this is a 220K resistor. It's pretty simple. Okay, lettering for colors. Let's take a look at what's going on here. So essentially, there are two kinds of color codes for resistors. One is a 4-band color code and one's a 5-band color code. We're going to walk through how to do both of them. A lot of them are going to be 4-band, but essentially once you know how to do 4-band, it's easy to do 5-band. You just need to know a couple things. So let's move forward. What we got here is we have all of these bands and they have meanings and purposes to them. So the first band, and I will tell you later how you can identify the first band, but I think you'll figure it out as we go. So the first band is going to be a number. The second band is also a number. So depending on its color, it's associated with a specific number. So if it's a 100 ohm resistor, the first band will, the color of that band will be associated with the number 1. We'll see what color that is later. So the second band also is just a number. So if it's a 22 ohm resistor, those two colors will be the same. Now, if it's a 220, well, what do we do about that? We need to add a 0. This is the multiplier. This tells us how many zeros we add. And then this guy is the tolerance. The tolerance has to do with how well the manufacturer produced this resistor. So essentially, what's going on here is that if you're a manufacturer and you're manufacturing something, how accurate is it? Well, it all depends on your manufacturing process. It's also limited to whatever you're using, the tools you're using, or more specifically, the materials you're using to build these things. So it's really difficult to build one of these. It's like 0.01% accuracy. I've actually never seen one that accurate. I've seen them that are 1% accurate, 5% accurate, 10% accurate, and some of the older ones in the circuits are 20% accurate. And sometimes you don't really need them to be that accurate. So, because you've got those trimming pots, and there are other reasons why, but we're looking at color code, so let's move on. This last digit tells us how accurately it was manufactured. Okay, let's take a look at the numbers and the color codes. So again, the first two digits are just numbers. So in this case, I've got a brown and a black. So let's take a look at it. Brown is 1. Okay, black is 0. Okay, so the value of this is 1, 0. Now, how many zeros do I add on? Well, I add a red. Okay, so red is over here. This is where I go to my multiplier. Oh, red is 10 times 2, so I'm adding 2 zeros. So it's 1,000 ohms. How accurate is it? Well, this is silver. Okay, so silver's over here is 10%. So this guy is 10% accurate. So if it's a 1,000 ohm resistor, it actually could be anywhere from 900 to 1,100 ohms. Yeah, not perfectly accurate. Silver is 10%. Again, if it's got no band, it won't have any it's just 20% accurate, but you really won't see those unless you pull an old circuit apart, because newer manufacturing processes are accurate enough that they're always at least 10% accurate. So there you go. So this is how you do it. Start with the band closest to one end of the resistor. Okay, so what's happening is here, how do you know which is the left and which is the right? So there's a gap in here. There's a gap in here. So you know that this is the tolerance band, and that's the last band. So you start with this band and you move forward and you read it this way. The first digit, the second digit, the multiplier. So, and then this guy over here is all about the tolerance. So when we're looking at tolerance, there are kind of two different kind of words that we need to use. One is the measured value and one's the nominal value. And the nominal value is what you've just read off the code. So that is whatever the numbers are. But again, it's not going to be exactly that. But that's the nominal resistive value. That's what it's labeled as. But when you measure it, it's the measured value that you're looking for. Ultimately, that's really important. And that is the value you're going to put into your formulations if you're doing further formulations after you build a circuit. Now, I just wanted to say that carbon composites, they'll often not have a space here. So you kind of got to think to yourself, whoa, which is the first band and which is the last band? You flip it one way or flip it the other, and it's the same either way. So there are kind of ways to figure that out, and we'll look through that when we go into a 5-band resistor, because it also has that same kind of problem. There's no gap in here, and you don't know which is the left and which is the right. Okay, so let's just take a look at an example here. So I've got my first band, it's brown, so it's going to be a 1. My second band is black, so it's going to be a 0. And again, the third band is red, so I'm going to add 2 components, the same one we just looked at, but this is actually just walking you through with some values here. And then this one, the silver, is 10%. So what I'm going to take a look at is the upper range and the lower range. I want to know if this is 10% accuracy, or the tolerance is 10%, what could the possible values be? Now, this is a 1,000 ohm resistor. So if we actually just kind of take a look at the tolerance on this, we can see that I have 10% up and 10% down from my nominal value. So the resistance of the nominal, I'm going to go 10% up and 10% down. Now, what this is like a formula. You just figure it out however you want. It's pretty simple. I mean, you don't need to go through this step by step, but I'm just showing you mathematically how this is done. But you know how to find 10% more of a value and 10% less than a value. So there you go. That's the tolerance, and I think it just makes sense. So some examples here. We can go through all of these because I think it's important just to kind of run through this a little bit more. So I want to know if all of these are going to be 5%, how do I find out what the numbers are? So a 2.2K, how do I define what a 2.2K is? It's going to be red, red. Let's take a look at why that's true. So I've got 2, 2, so red, red. So my first two digits are going to be red. First two colors are going to be red and red. And then after that, I've got to make sure that I add the right amount of zeros. In this case, I want to add 2 zeros. We added 2 zeros before, and we can look here, and that's a red as well. Oh, okay. So for this case, it's going to be red, 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 and then gold. Why gold? Because it's 5% tolerant. Okay, good. So let's do this next one. So the next one over here is going to be 56K. So I'm going to do 5, 6. So 5, 6. Okay, I go down to 5. That's green and blue. So it's going to be green, blue. Then I've got to add 3 zeros. I've got to add 3 zeros. So that's going to be orange. Green, blue, orange. Again, gold. Now, this last one over here. Okay. What do I do here? I've got 10. I'm going to definitely have a 1, so it's going to be a brown, and then a black, and then I just have to add a certain amount of zeros. So how many zeros do I have to add? I got to add 3 zeros plus this 0, which is 4. So I'm going to rewrite it here. So I can identify this value and this value because I have a color for black. I mean, I have a color for 0. So in this case, I'm just going to add 4 zeros. So I go down here, 4, it's going to be yellow. Okay, so black, brown, brown, black, yellow. Okay, so this is going to be 39, so I'm looking for 39. So it's going to be orange, and it's going to be white, and then I'm going to add 6 zeros on top of that. The 6 is blue, orange, white, blue. Awesome, orange, white, blue. And over here, this is an interesting one. I think we got to pause and kind of think about this one a little bit. This is 2.2 ohms. Okay, what's the multiplier? It's interesting. I know it's going to be red, red, for sure, because red is 2. So it's red, red. But how do I add a 0 here? I don't. I have to put the decimal back this way. Ultimately, I'm multiplying it by 10 to the whatever the number is, which is easily just saying that's how many zeros I'm adding. But I'm shifting the decimal that many ways. To do that, I'm going to say times 10 to the minus 1. And that happens to be one of my multipliers, which is going to be a gold. So I'm going to red, red, gold, gold, and then another gold, if that makes sense. So let's take a look at 5 band resistors. 5 band resistors are just for more accurate or precise values. So I've just got some examples here. The only difference here is the fact that you've got to figure out which side you start counting with, which is a little tricky, and I'll tell you some ways to do that. But the reason that we've got 5 is because I have an extra band here, or a third digit, that gives me more accuracy. So I can have a 222 ohm resistor if I wanted. Yeah, let's take a look at some examples. Now, oh, by the way, before I move on, all of these are always 1%. I mean, because if I'm getting something that's that precise, I want it to be precise anyway. When I said all of them, I lied to you. I've never actually seen any that aren't 1, but supposedly there are. I've never seen them, but I guess there's some of these that are maybe 5% accurate. But if you're designing a resistor to have 3 significant digits of accuracy, you're probably going to build it out of whatever material and use whatever machine is happening in your manufacturing plant that you're going to build it that accurate in the first place. So most of these are going to be 1% accurate or tolerance. So let's take a look at this. So I'm just going to have red, red, green. So it's 225. And then my last one over here, this is going to be my multiplier. In this case, it's gold, so it's times 1 to the negative 1. Often you'll see this. Often for a 5 band resistor, they want to get that decimal in there. So in this case, it's 22.5, and then it's times 10 to the negative 1. So in this case, what we're going to do is we're going to change this to silver if we're going to do times 10 to the minus 2. So if I wanted to do 2.25, then I would have to just change the multiplier. But for 22.5, I'm going to use gold, because if I go here, that's gold. If I want to do 2.25, then I want to switch it over to silver, which indicates I'm switching the decimal that way one more time. So 2.25. There you go. So yeah, let's move on. And here we go, 5 band resistor. Another example of what's going on here. And we're going to have a 4, a 7, and a 0. Okay, 470. Now, in this case, I'm not adding a third digit that's like 473, 472, 471, whatever. I'm not actually adding 470. It's important to note that that 0 is a significant digit. If it's there, it means that's a 470. Like it's exactly that much. Again, that's just the other reason why we see these things at high precision. Because if you're adding that 0 there, that means you want that value to be really close to 0. It's not going to be 5. It's not going to be 4. You want it to be close to that value. So that's where we're looking for. It's going to be brown. It's going to be 1%. So I just have my 3 digits, and then on my multiplier, in this case, I've got a 470 ohm resistor. My multiplier is actually just 10 to the 0. So my multiplier is going to be black because 10 to the 0 is 1 because I don't want to add a 0. There you go. And then again, it's brown. So now just this is just another example here where my third digit is going to be 5. And in this case, my orange is 3. So I'm adding 3 zeros. So I'm putting a kill onto that. Now, I want to talk about how you know which is the left side and then the right side, and then everything's done, and then we're done. So let's just talk about this. If on a 5-band resistor, how do I know which is the left and which is the right? Well, essentially, what you're looking for is you're looking for the multiplier so the tolerance on one side or the other. Now, the tolerance actually can only be brown or gold. So when you're looking at a 5-band, just look for the brown. And you'll be like, okay, well, that's the right side. And then just start reading from there. Now, the only problem is, what if it starts with brown on either side? How do you know which is left or right? Well, you have to guess or just measure it. But essentially, this is an example here. If I had brown, red, black, orange, brown, well, which is the multiplier or which is the first digit? And then which is the tolerance? How do I know? I don't know. There are 2 ways to look at that. You could read it like this. So that's going to be 120 times 10 to the 3. 120, or it's going to be, if this is the first digit, it's going to be 1, and then I'm going to have a 3, and then I'm going to have a 0, and then my multiplier is going to be 2, and then my tolerance is going to be 1. So how do you know? Just measure it. So that's it. So that's pretty rare that you're going to see that. You might not even come across that in your whole life, unless you're using these all the time. So that's all I have to say. Yeah, I think we're good. I think we're like, you can roll with this and figure out how to do this. It's just about practice. Okay, bye.